ourselves. No, about what a reference angle is. So, the reference angle for an angle in standard position is the angle between the terminal arm being the arm that you've drawn on your grid, wherever it is, and the nearest x-axis. Remember, standard position angles always went from the positive x-axis. Reference angles go to the closest x-axis, and it can go in any direction to the closest x-axis. So there should be, four different reference angles that can all actually be the same. And I'm going to show you how that would work. So we're going to draw a 30-degree reference angle. A 30-degree reference angle could look like this. That's the angle between the terminal arm, correct, and the nearest x-axis. Correct. But I could draw that exact same reference angle to other x-axes. So I could draw it like this and say that's 30 degrees as well. That's still a 30-degree reference angle in between terminal arm, closest x-axis. It's probably pretty obvious that I could do two more of these. I just go down. And if I just go good question. That comes from the definition, which says that you have to go to the nearest x-axis. So if I was down here on this blue line, and I wanted to make an angle, the closest x-axis would be this guy, not all the way over here. The biggest mistake people make when they talk about reference angles is they go to their y-axis. Right? And that's where people get screwed up. They want to be like, right here, that's a reference angle of 30 degrees. That is not a reference angle of 30 degrees because it's going to a y-axis, not an x-axis. So make sure anytime there's a little reference, you're always going to the x-axis. We don't really go to y-axis. Every once in a while, but only in specific examples.
Well, it looks like it's kind of in the middle, unless it's supposed to be kind of.
What do you mean?
Oh,
it's just no. Those look more like 45s. Yeah. And this one might even be bigger than 45. They're just sketches.
Where would you go?
Right in the middle, but it.
No, I mean near nearest x-axis. Okay, where's the?
So, if you talk about 45, I'm just going to erase this. Everybody got these down? Okay. But 45, think about it. This is 45, correct? I have two x-axes. I have this guy and this guy. So which one would be the nearest x-axis?
Oh,
this guy. This would be 45 to the nearest y-axis,
okay.
Which is why I'm saying people screw it up, right? Because they go to the y-axis. Okay, that's a new question. I'm going to bring that up too.
Just go to either.
Okay, so that's the question that Danny just asked too. What if your terminal arm is like straight up like that?
Possible.
Right? It's possible. I would just go to my x-axis there, but you wouldn't be wrong to go the other way.
Okay.
So you could go either way because they're both 90. This would be 90 degrees and this would be 90 degrees. So you wouldn't be wrong either way. That's not going to happen. So don't worry about that. But if you did have to do a reference angle that was at 90, then you could go either way and you'd be fine. It's just that one. That's not cool. All right. Those angles. Oh, I should delete it. Okay, now quick draw again. We had this one, that one, and they were all 30 degrees, correct? All right. Look at question B. Question B says, state the standard position angle for each reference angle. Standard position means from the positive x-axis, counterclockwise, to the terminal arm. Let's do the first one. From the positive x-axis, counterclockwise, to the terminal arm. In quadrant 1, the standard position angle is 30 degrees. It's the exact same as the reference angle. That's why yesterday, or 6.1, was a little bit easier, because our reference and our standard position were the same thing. We weren't having to mix the two definitions together. But in quadrant 2, if you look, my standard position is going to go from right there all the way around to right there. And they're talking about this big green angle as their standard position angle. The way you're going to calculate that is by using a little bit of your conceptual ability and a little bit of logic. If I went from here all the way to here, the other x-axis, how big would that be? If I went all the way across, that would be 90 plus 90, that would be 180 degrees if I went from one x-axis to the other axis. But I didn't make it all the way to the other x-axis. How much short did I come up? So if you go 180 minus 30 degrees, that'll tell you your standard position angle. That green angle is 150 degrees. Because the reference angle was 30, that would add up to 180. Let's do quadrant 3 standard position angle. I start at my positive x-axis. I go all the way until I hit my terminal arm. Now I went all the way to 180, and I went an extra 30. So my new standard position angle for that one would be 180 plus 30 for 202 degrees. Do you see how that's working? I went all the way to 180, which was this spot right here. And then I added an extra 30 to get to that terminal arm. The one before, I went to 180 minus 30 to get to the terminal arm. I want you to try quadrant 4. So see if you can find the standard position angle that would give you a reference angle of 30 degrees in quadrant 4. So you're looking for that big guy. Give it a shot on your own. Give it a shot. See if you can logically think your way through it. Okay. If I'm looking at this standard position angle that went from positive x all the way around to this terminal arm down here, the only thing I know is that this inside is 30. Whoa. This inside is 30. If I had done a full circle all the way back to the starting point, how much would have that been? Would have been 360. But I didn't make it all the way around to 360. I made it 360 minus 30. So your answer would be 330 degrees. That seems maybe really easy right now. You're gonna mess it up. Okay? Practice it. Like, don't just take this stuff for granted and be like, oh, this is so easy. Like, you're gonna make little mistakes. It's really easy to be like, well, you go to 270 and add 30. Right? Like, people do crazy things when it comes to this stuff. Practice, practice, practice. That's definitely the key. No. It's coming, don't worry. All right. In all 4 of these questions, I want you to write what the standard position angle is. So the standard position angle for all those diagrams. You can give it a shot on your own. Finding the standard position angle. That means you're finding the angle from the positive x-axis to the terminal arm. In this case, it's right there, which is the same thing as your reference angle, which is 35 degrees. Question B. You want to find the standard position angle. That is your positive x-axis around to your line. This one would be 180 minus 35. So the standard position angle will be 145 degrees. Right? Go all the way to 180, back up 35 to get to that terminal arm. This one, the standard position angle would be all the way around to here. That would be 180 plus 35, which would be 215 degrees. The last one, right here, all the way around to there. That would be 360 minus 35, would be 320. How are we feeling? Decent? Good. Let's knock out the basics and we'll be set. Okay, let's try to draw some. So they have now given you an angle and they want to know what the reference angle is. For all of these, what you should have is a beautiful XY axis in the middle of each of these. You draw it yourself. I'll draw the first one with you, and then I want you to try the next two on your own. So, for an angle of 155 degrees, 155 degrees, up here is 90, over here is 180, down here is 270, and all the way around is 360. 155 would look somewhat over there. It's a full-on estimation. That 155 degrees is right in there. It's in quadrant 2. Everyone's good with my drawing? The reference angle. The reference angle for this question is right there. That's what they want me to calculate. In this case, I want to picture, what if I went all the way around to 180, but erased out the 155? If I did that, it would give me this reference angle, which is 25 degrees. So I went all the way to 180, and then I subtracted out the standard position angle, leaving me with this reference angle chunk. Yeah?
So it would be get reference angle about 180.
No, this one's reference angle about 180.
Yeah.
A reference angle. Yes, sorry. Reference angles are always in between 0 and 90. Always. So if you get one above something like that, then you should know you made a mistake. Yeah. Okay, I want you to try drawing number 2, and I'll help you calculate it, and then we'll do number 3 completely on your own. But try to draw number 2. If I was to draw this angle, it sometimes really helps to remember that the top is 90, the side is 180, bottom is 270, all the way around is a 360. 235 would be in between 180 and 270, so I would draw it like that. Reference angle means from here all the way to there is 235. That's my standard position angle in green. My people got the drawing good. It's just an estimation, right? Like, it doesn't have to be a perfect angle. It's just somewhere in quadrant 3 is good. They want you to calculate the reference angle, which is this little guy here. To figure that out, you have to think to yourself, if I went all the way around to 235, but I subtracted out the 180. I'm going to highlight in red. It would leave me with this little chunk right there, which is the reference angle. So 235 minus 180 is 55 degrees. If, and I'm just going to show you a common error, you went 270 minus 235, which is what a lot of people would like to do on a test. 270 takes you all the way to this y-axis. And then subtracting 235 would leave you with this little chunk in here. That's not a reference angle because that's to the y-axis. Okay, so make sure you're actually picturing what you're subtracting and adding. It sometimes helps. This one would be 235 minus 180. So all the way to the third quadrant, subtract off the top half. Leaves you with the reference. Try number 3 all on your own. So draw it, label which quadrant it's in, and calculate it. Drawing this thing. I want to be in 310 degrees. The very bottom is 270, the right is 360, 310 would be somewhere in there. Oh, 310, 10 pizza hut. The quadrant is quadrant 4. The reference angle is this little guy up here. To figure that out, I would do a full circle, 360 degrees, and subtract out the 310 degrees, making my reference angle 50. Doing good? Awesome. Okay, we have one more, and then we're going to move on to something different, so a little bit of negative angles. This one is determine the angle in standard position in the second quadrant that has a reference angle of 48 degrees. I want you to try this one fully on your own. Don't help each other. Don't ask for help. Just see what you can come up with. Okay? Determine an angle in standard position. That's a keyword. In the second quadrant, that's a keyword. For the reference angle of 48, that's key. So I want you to try it on your own. Don't tell anybody any answers. Don't ask any questions from anyone yet. Because as this trig continues on, it's going to get more and more complicated. The best thing you can probably do to help yourself is draw. Then you won't fall for little mistakes. Okay, so we are going to draw this out. They want to calculate an angle in standard position in the second quadrant. Alright, so in the second quadrant, I'm looking for an angle in standard position that has a reference angle of 48. Reference angle means to the closest x-axis. That would be this guy right here. If I want to figure out the standard position angle, the green angle, then I would go 180, because that would get me all the way across, and then subtract 48, because that would erase this portion out. And my answer would be 132 degrees. That's the standard position angle that gives a reference angle of 48 in the second quadrant. So the answer would be, oh, I started the wrong one. The answer is C, 132. Okay, now we're going to start going backwards. So we're going to learn that standard position angles can actually also go counterclockwise, the wrong way. If you're going the wrong way when measuring a standard position angle, then you're doing negative angles. Alright, so here's an example right here of a standard position angle that's at negative 160 degrees. It went the wrong way off the positive x-axis. Standard position typically goes that direction. So if you're going clockwise this way, then you're going negative angles. Simple concept. So this terminal arm right here actually has two different standard position angles. It has negative 160, but it also has another angle that can go from here to here. What would that be? You ask your question first. We're going to get there. We're going to get there in a second. This standard position angle would be negative 160 degrees plus 360 degrees. Because that would take me from here all the way around. That means the other standard position angle that would get me there would be 200 degrees. That would be the other standard position angle that gets me there. Right? Negative 160 brings me back to here. Plus 360 brings me back all the way around. It's a trippy concept, I know. Alright, in this diagram, you don't usually have to go in between two standard position angles. You might, but I just want you to see that you could measure standard position angles two ways. Positively and negatively. Now, we're going to try to find the reference angle of this beautiful standard position angle of negative 160. The reference angle is between the terminal arm and the closest x-axis. That guy right there. That's the reference angle. Reference angles are, by definition, always positive. So it doesn't matter which way you go, reference angles are always positive. That clear? Only standard position angles can be negative because they can go backwards or forwards off of this axis. Reference angles always go to the nearest x-axis, so it doesn't matter which way you go, they're always positive. If I wanted to figure out what that missing angle was, there's a few strategies that you could use. I like to think of things as it took me 160 to go here. If I wanted to come all the way to here, how much more would I need? I would need 20 more, right? 160 gets me to the terminal arm. How much more would get me to 180? 20 degrees would get me to 180. You could also use the positive value of 160 and just flip this image upwards to think of it like that too. That would work the same way. Yeah, Joe. Does that make sense that it's 20? When it gets into negatives, it gets trippy. That's why understanding about the 180s, the 90s up here, the 270s down here, that's for positive. If we were to go a negative, this would be negative 90, negative 180, negative 270, and both of these are 360. It's basically like being flipped upside down when you're finding reference angles. It's easier? That's good. Hey, you could have done that for the other ones too. Alright, we have 4 right here. I'll do the first one with you. I want you to sketch each of these. Sketch the standard position angle and the reference angle. They've given you the standard position angle for each of them. Negative 45. Well, negative means I'm going this way. This would be negative 90. So that means my angle should be something like that. That's negative 45 degrees. That's the standard position angle. The reference angle is the angle between the terminal arm and the closest x-axis. It's the same distance. It's the same angle, except reference angles are always positive. So the reference angle is positive 45 degrees. Okay. Angle standard. standard position angle because they put in the last next to it. They don't need to, but they're just trying to make it clear that that's standard position. Any questions about that drawing? Right? Standard position backwards, reference angles between the x. Try to find that reference angle. Do the next 3 on your own. Give them a shot. We want to do one more together. I'll let you.
Yeah.
One more together. Okay, we'll do one more together. Standard position is negative 150. Negative 90 is straight down. Negative 180 is to the left. Negative 270 is up high. Negative 150 would be somewhere in here. That's negative 150 degrees as a standard position. They want to know what the reference angle is. This guy right there. That means they're asking how much more would it take to get to negative 180? Well, it would have taken 30 more to get there. You could do it mathematically by being 180 minus 150 equals 30 degrees. Or you could look at it logically and be like, how much more do I have to get there? Right? Whatever works for you. It's a little tricky when you get to the negatives because you should be going minus negative 150, but then you'd be adding, right? So you take the absolute value or the positive version of the standard position angle. Okay. With this in here. Oh, yeah. Think that you have to go in a full circle, right? So you start at 0. Like 0 is the initial. And then you go negative 90, which would be here. And then you go negative 150, keep going that way. You have to end up down. I'm sure if that answers your question or not.
Yeah, it's just...
It's confusing. Yeah, I know, it is. That's why I keep saying, like, if you need the basics because it's going to get hard, right? Negatives get confusing. So it's okay if you're kind of like, whoa. It's a little trippy. Okay, now try the next one. We'll do C together. So if I want to be at negative 210, this is negative 90, negative 180, negative 270. My angle should be somewhere up there. In between negative 80 and negative 270. The reference angle is the gap between the nearest x-axis and the terminal arm. To get to this nearest x-axis, I would have had to go negative 180. I need an extra something to get to negative 10, or 210. What's that little extra gap? 30 degrees is that little extra gap. Right? I went all the way to 180, a little extra 30 gets me to 210. That's against it. Do you know where 60 would have been?
Yeah, I just was looking at the wrong. I was looking at the longer version. I get it now though.
Yeah? Oh, like why did I not fall in here? Like that? You always start at the positive x-axis? Oh, I drew it like that. Sorry. Yeah, you can go both ways, I guess. You should start there and go like that. That's my mistake. I didn't think of people watching me draw. But yeah, you should go from here all the way around. I noticed that it's the same distance. So that's my fault. Always start on the positive x-axis and then go towards the terminal. Negative means go down, positive means go up. That's my bad. I never even thought of people watching me draw angles. Okay, D, if you did that one, 300 would be somewhere up here. Ready? The reference angle would be this little gap in there. It would take negative 360 to do a full circle, but I'm missing this little gap. So I made 300, and then I would have needed 60 degrees more to get all the way to that next x-axis. Pardon? Down to negative 90. Over here to negative 180. Up here to negative 270. Up here to negative 360. Just the top and bottom ones. All right. Yeah, I think we're going to finish thing out this way. That's positive and negative angles, standard position, and reference angle. Now, what we're going to start to do is we're going to start drawing triangles. Okay? When we draw triangles, you're talking about reference angles, right? Because remember, our angles were always 90-degree triangles whenever we're doing SOHCAHTOA. So we're always talking about reference angles. I'm going to draw some examples of triangles in here. Then I'm going to teach you something, and then I'm going to teach you some complications. Okay, but I would way rather logic prevail than this thing called the cast rule. So what we're going to do is we're going to draw triangles with reference angles in each of these 4 quadrants. Feel free to write it down if you want. You don't have to. It's more of a conceptual thing anyway. So if I was to draw triangles with reference angles in all 4 quadrants, they would look like this. That would be a reference angle. That would be a reference angle. That would be a reference angle. This would be a reference angle. It's a nice little bow tie. A crooked one, but a bow tie. That's 4 triangles, all with the same reference angle, but in different quadrants. If we were doing SOHCAHTOA in all of these, think about just the values you'd be using. In quadrant 1, my y value would be a positive or a negative number. It'd be positive because I went up into quadrant 1. What would the x value be? Positive. So, if we did SOHCAHTOA in the first quadrant, sine equals opposite, which is y, over adjacent, which is x. That would be a positive divided by a positive, which means the sine ratio would be a positive ratio. And then y over x. Also over hypotenuse, which is a positive as well. For the record, r is always a positive number, so the hypotenuse is always a positive calculation. You're way too far ahead. We're getting there, man. We got to build. So sine was opposite over hypotenuse, y over r. That means positive divided by positive. Sine ratios in quadrant 1 are always positive. If you tried cos, the cos ratio is x over r. In quadrant 1, what is x? Positive. What's the radius? Positive. So you're talking about a positive over a positive. That means the cosine ratio is positive in quadrant 1. The tan ratio. Tan ratio is opposite over adjacent, which is y over x. That means you have a positive over a positive. The tan ratio is positive in quadrant 1. All 3 ratios, all 3, are positive in quadrant 1. That's not true in the other quadrants. Because when you look at these ratios, When you look at the ratios in the other quadrants, you're going to start to have negative values. No, your R value is always positive. Always. Yeah. And that's important to know. R is always positive. Not automatically. Okay. Coming over here into quadrant 2, we're going to look at the ratios. So, the sine ratio is y divided by r. Looking in quadrant 2, what would my y value be? It would be positive, right? Because we went up. What would my x value be, though? My x value would now be a negative because I went to the left. And r is always positive. So, in quadrant 2, sine is y over r. My y value is positive. My r is positive. That means sine is positive. If you look at your cosine ratio, cos, which we calculated the other day, is x over r. X in quadrant 2 is negative. Divided by r, which is a positive, and negative divided by a positive results in a negative. So cosine ratio is actually negative in quadrant 2. Tan ratio. The tan ratio is opposite y divided by adjacent x. That would be a positive divided by a negative. That means the tan ratio is negative in quadrant 2. In quadrant 2, only one ratio is positive. Which ratio is it? The sine ratio is positive in quadrant 2. Yeah. Yeah, you're under attack. You completely have. Yeah. The way that we calculate R is what makes R always positive. So remember the formula we made for R? R was equal to x squared minus y squared. Squaring both those numbers forces it to be positive. And then you square root the number, it has to be positive. So R is positive just by the nature of the formula.
Like, why is that? Why is the...
Because I went to the left, right? Think about this as a graph. If I go left, all these x values are negative. No matter how far left I came, it's a negative x value. So I built a triangle, right, based on a point that went up and then to the left.
It was going to x axis and y.
Yeah.
So like, between x and negative it's just based on how you do this.
Yeah, like that's, I just put myself up here. Like
You're
this
just trying
point,
to build up to that.
this point up here, yeah, like that is a triangle based on that point. That point had to go up and to the left. So it's positive and negative. Anything in quadrant 2 will follow that same pattern.
So like those ones are going to be going down.
So they'd be negative and negative.
So, like this, right, R is always positive.
R will always be positive no matter where you put it. Always. So, looking at quadrant 3, that means if I built a triangle down here in quadrant 3, I would have had to go negative to the left and negative down, giving me a negative x and a negative y. That means sine, which is equal to y over r, and r is always positive. I would have a negative divided by a positive. My sine ratio would be negative overall. It would be a negative number. My cos would be x over r. That's negative divided by a positive. That's negative overall. And tan is negative divided by a negative. It's y over x. Meaning that it's negative divided by negative equals positive. The only ratio that was positive in quadrant 3 was tangent. cosine. Sorry, I'm way ahead of myself. Quadrant 4. If you look at quadrant 4, it's positive in the x-axis, but negative in the y-axis. The r is always positive. You do all of your ratios, and you're going to end up with sine equals a negative over a positive, which is negative. Cos is going to be positive divided by a positive, which is positive, and tan is going to be negative divided by a positive, which is negative, making the only positive ratio in quadrant 4 cosine. All right. The reason that's important, those triangles that we built all have the same reference angles, which means they actually have all the same x, y, and r values except for the positive and negatives. So I built that same reference triangle in all 4 zones. There's going to be examples where you need to know which zone you're building your triangle in. The best way to remember is by using something called the cast rule. The cast rule tells you where ratios are positive. So, we built the word cast. Cosine was in quadrant 4. That's where cosine is positive. A is for all quadrants are positive, or all ratios are positive. S means that sine ratio is positive. And T means the tangent ratio is positive. We're going to see examples of how to use this, but that's how the cast rule works, based off those positives and negatives that we just did. Does anyone have any questions about why ratios are positive or negative? Not how it looks in an example, but how, okay, I get the tangent is negative because it's y over x, positive over negative is negative. Does that make sense? Good. Let's try an example. Here's 4 examples. The angles in standard position state the quadrants in which the terminal arm of the angle could lie. Could lie. Sine equals 4 over 5. We know that sine is equal to y over r, right? Using our TOA knowledge. On a graph, that means this triangle could be right here. Right? That would be 4. That would be 5. That's possible, correct? There's somewhere else I could build that triangle. Where else could I build that triangle? Which quadrant? Quadrant 2. I could build that. Because y is 4, r is 5. See how that works? Another way that I could have figured that out really simple. Your cast rule tells you where ratios are positive. Sine equals 4 over 5, that's a positive number. That means it could have been an S for sine is positive, or A for all are positive. So that's a quick way to tell which quadrant you could have been in. I much prefer this method. I also understand that some people don't like this because it's a little bit more complex. It takes a little bit maybe more knowledge of what's happening. And some people just like to rely on cast. Your choice, okay? But I prefer you to understand how it's working. Yep. If this was a question on a test, and they said, draw the angle, you need both. Both are correct. That's why they said could lie. Right? Both of these are possible. You don't know which one's right, you don't know which one's wrong. So both are the right answer. You need both there to be correct. Yeah. Good question. So let's try cos. So cos of alpha equals negative 1 over 2. That means cos equals x over r. What do we know about r?
It's positive.
It's always positive. That means when you go to build your triangle, you have to be building it where x is negative 1 and r is 2. I could build it here because that would give me negative 1 and 2. Where else could I build it? Quadrant 3 I could build it because that's negative 1 and 2. Both triangles are legit for cos equals negative 1 over 2.
Is there any times when you're doing this where you can't use like cast?
Cast rule will always work. Yeah, that's why I'm okay teaching. If you think about cast rule for this question, you're thinking about the opposite. Cast tells you where things are positive. In our case, cosine is negative. So cast told me cosine's positive here and positive here. So if I want it to be negative, I have to be in S and T, right? The opposite. So it's kind of thinking backwards. The cast rule? Do you get the other way? Do the other way. You don't need to know the cast rule. Yeah.
So why is it
Cast is good question. C stands for cos, A stands for all, S stands for sine, T stands for tan. So it's telling you which ratios are positive. So in quadrant 4, cosine's positive. In quadrant 1, all are positive. Quadrant 2, sine is positive. Quadrant 3, tan is positive. So the letters stand for which ratio is positive. They gave me cosine, but cosine's negative. So where could cosine be negative? Yeah, so if tan was negative, then I'd be in sine and cos, right? Because it's not positive. It's like thinking opposites. Does that answer your question? Yeah, like opposites. Okay. Yep. Oh, so the answer would be right, 2 and 3.
Okay, so could you write the numbers?
Definitely. That's what I'm saying. You could use the castle to answer it really quick, or you could draw pictures to
Is
answer
it
it.
going to be like on this axis? Is it going to be like some sisters as
Nope.
your answer?
No, it would just.
2 and 3.
I'm going to be completely honest. If you got a question that said which quadrant are you in, you should be very happy. Yeah, like this is going to get maybe.
Really?
It might be draw 2 possible triangles and solve them.
But
like-
like make the question a little harder.
Yeah.
It won't be like, where is it? It will be like, no.
We got a lot to go still. We're still going. Like we're building, right? Think about it as like standard position angle. We learned that definition. Seemed pretty easy.
Yeah.
Reference angle seemed pretty easy. And then like we're building up to actual questions. We're not there yet. If you get a question like this, like that's a good question. That's it. You should be really happy. Yeah. All right, down here, tan equals 1 over 5. You need to know that tan equals y over x. That means positive 1 over positive 5, right? That would make sense. So that could go up here. 1 comma 5. However, the ratio was positive. What if I had negative 1 over negative 5? Those would have canceled to be positive overall, right? So that means the other place I could have drawn this triangle is down here at negative 5 and negative 1. That's probably the one people do the worst on. because they have a hard time realizing two negatives would cancel out to give me a positive ratio. Again, you could just follow the cast law. And the cast, you know what, it's called the cast rule. There's a difference between laws and rules. The cast rule tells me where things can be positive. Tangent is allowed to be positive in T and A. That's why it's in quadrants 1 and 4. Or 3. Tricky, right? Every triangle can be built in 2 quadrants. That's probably your probably go-to bonus. Every triangle can go in 2 quadrants unless it's otherwise stated. Try number 4 on your own. Try to write down the quadrants and show why. Try to actually draw them. D. Sine equals negative root 5 over 5. Sine is equal to y over r. R is always positive, so the negative must belong to the y value. That tells me I could draw my triangle in 2 spots. I could draw it down here at negative root 5, or I could draw it down here at negative root 5. Something I want to note on all my triangles that we haven't talked about, so maybe pay attention. What do all my triangles connect to? The x-axis. Never once have I drawn one to a y-axis. That's important because we're always using reference angles. So always connect to your x-axis in all your drawings, no matter what you're doing.
So they are 3 and 4?
They are in 3 and 4. We mixed up over how many quadrants is it in. That's why when you said they're in 4 or 2, I said it's only in 2 quadrants. And you guys are thinking it was in quadrant 2.